This video is made possible by the Eliason Group, an Agile consulting service. You can locate the video under Follow Us, then select Recent Videos on YouTube on the agilenewengland.org website.
Van Schooenderwoert. Her last name is longer than mine. I think that's really cool. So, Nancy is a really cool person. She's one of the reasons I'm here. I think of Nancy as a good friend. She has a great sense of humor. She's giggly, she's friendly, she's warm. She's why I'm here. She's why I'm here all with Agile New England, because they're friendly people like Nancy. I'm also really interested in Nancy's talk tonight because Nancy is, she's at the forefront of Agile for non-software projects, in particular Agile with hardware projects. I just started working with a group that's a hardware group, and we're seeing what we can pull from Agile to help that group succeed. So I'm really eager to hear what Nancy has to say about this tonight. And let's give it over to Nancy.
Hey, thank you, Rich. Welcome. This is going to be about hardware and software collaboration, right? Just like the title says. How many people here do we have that are working in a project that has both hardware and software involved? How many people are doing that? Oh, wow, that's most of the room. That's great. And how many of those are attempting to be agile, at least in some aspect? Oh, not too many. Okay, at least in some aspect. That got a few more hands up. Okay, probably the software, right, I'm guessing. And you're hoping the hardware people will come along with you. All right, I'm going to talk about that kind of thing. Let's see, first a little bit about my background. I've worked in safety critical hardware, software kinds of systems my whole career. And well, let me just say a little bit about that. Initially working in aerospace and flight simulation. I worked in, after that I worked in Navy systems, sonar systems, again, hardware, software, cooperating. I worked in factory automation, industrial controls areas, and I've also worked in instrumentation, specifically medical devices. And out of that work, well, really, as part of it, an integral part, I always had the opinion that defects are not something that just happens. We put them in. So to me, that meant we don't have to put them in. We don't have to put any of them in. Some people found that hard to accept. It's always been seen as a very, I don't know, radical idea. And I think it's just common sense. So I was working in these industries and finding more and more ways to keep defects out. So that kind of led me to the early Agile attempts that were going on. Before Agile came out in 2001, there were a lot of the practices that made it up were floating around, and if you were paying attention, you might have been using some of them. At least I was with contractor teams I worked with. But so I had a project. I'll take some examples from that tonight, and I'll mention some others. I had a project where I was working on a scientific instrument, a spectrometer, that might have medical applications. We had a medical customer in line for it. So I'll take some examples from that. I'm also going to mention a few other things. Let me move on here. This is a picture of a flight simulator that I worked on. Oh, what else? Let me just back up a second. What else I was going to say is, since the early 2000s, I've been working as an Agile coach because I didn't want to go back to doing engineering the old way. And that's all there was, because Agile was too new. You had to basically do it undercover. So here's a picture of a type of flight simulator that I used to work on. This is, the kind that they would use for training airline pilots or military pilots. Our company also had all of the NASA contracts as well. And the interesting thing about this was I came to this work with essentially a double degree. I started off working to be electronics engineer, in college, but there was computer science, and that was really interesting too. So I got a computer engineering degree after all, instead of just double E, which is really a combo of both. And the interesting thing about the the company that I went to work for is that the same engineers did the software and the hardware. We would lay out the flight instrumentation panels for each simulator. We would make the decision which instruments to use, real ones from the aircraft or to fake in, and just take out the electronics and drive the dials directly. We would make those trade-off decisions, and we'd figure out what mattered to pilots. So we had to work very closely with a certain amount of human factors and a certain amount of training. I mean, after all, the whole product we were building was a testing device, really. It was a way of people testing whether they could fly an aircraft adequately. Okay, so the interesting thing there is there was no separation between hardware and software, and to me, that was how it should be. I wasn't used to the idea that a different group should do software. In fact, a few years into our work, there was a rumor going around that the company was going to bring in a manager who was going to have a different group do software and hardware. And I remember us engineers talking about it and saying how ridiculous that would be, and it would take the fun out of our job. Little did I know that when I moved on working other places, I found out everybody else in the world separated the two. So anyway, I guess I have an unconventional attitude about hardware, software being separated and done by different groups. But anyway, that's the way it is, and the specialties have gotten deeper, so I'm not really fighting that so much. Let me pause just for a little item here before I jump into our topics today. Feel free to just stop me if you need a clarification or you have a brief question. If you have a more in-depth question, I'll deal with those at the end, if that's okay. But if something's just burning, go ahead and raise your hand, and we'll see what we want to do. All right, let's see. Okay, so here's what we're going to talk about. I wanted to get into what kind of things get in the way of hardware-software collaboration. I've listed 3 key items that seem to always come up when I have conversation with people or when they're asking me about this. The deeper specializations, it's a little harder to cross-skill. The longer hardware cycle times, that seems to prevent the whole notion of short iterations. And the business about rework, it seems that since hardware is a lot harder to change, that you have to have a planning phase up front. People don't see how you can dispense with that or how to shorten that up without losing something valuable. So I'm going to talk about each of those. My favorite part of this talk is the benefits that surprised us. Now, when my team that worked on this spectrometer project, when we started off, we were expecting to have higher quality and shorter development time. There was a bunch of benefits we were working towards, and we expected to get them. And we did get them, but the surprise ones are, to me, even more interesting, so we're going to talk about that. I have some tips and caveats that I would like to mention in closing, okay? So this is where we're going to start. Okay, let's talk about cross-skilling. How many people try to do this? I see pretty much all the hands going up, right? Have you had any luck between software and hardware cross-skilling? No, I'm not seeing any head nods, a little bit of maybes, okay. Yeah, so when the skills overlap, like they do in software teams, and even for teams and software testers, there's a certain amount of overlap. When they overlap, that works all right. And using a storyboard or a Kanban board helps you to see your shared work pretty well. Here's an example of a simple one. You can see that there's, we got the sprint backlog visible. You have a ready column, the work that's being done, actively done in the doing column. Done means the team thinks it's done, but the real done is when the product owner thinks it's done. Okay, so the assumption here is that everybody can work together and most any team member can help move any story along. It's kind of the assumption, right? Well, okay, what if that assumption doesn't hold true? Does it mean that the storyboard just can't help you much? Does it mean you should just work as separate groups, like in separate places? I would say no, it doesn't, because, okay, let's look at a picture where there are different groups. And by the way, this is a pattern that I've seen happen before. I've seen it not just with software, hardware. I'll give an example. A company where I coached years ago, they had an operation in-house where they printed up letters and monthly statements to customers. So they had printing machines and they, did the paper handling and the mailing. And the project was to outsource that to a vendor to just do all of that. And so on the team, we had a few people from operations and a bunch of other people from IT. Why? Because they're going to have to change their operation, their operations methods, and IT was going to be involved in the one-time transfer of the files and then setting up how to transfer them repeatedly. So they quickly discovered that there was a set of stories that only the ops people could work, and another set of stories that only the IT people could work. So we thought, does that mean we should have two separate storyboards? Well, you could. But we thought it was better to just make it visible. Why not just let the visibility show more readily that one sort of work has its own lane and the other has its own lane? It's okay. It's usually a good instinct to follow, is to always just make the work more visible when you're unsure of something. It tends to drive the right behavior. So in this case, the idea is we're still one team, so why not keep everything on one storyboard? It was still a pretty small team, even though we had some people from two different disciplines. But this could just as easily be a hardware and a software team. You could have a couple of electronics engineers working together with a small group of software and firmware people. And there would be this kind of a split with the stories. And they'll each have their own lane. It just helps it be more visible. You can take that another step further by looking at grouping them. See, this shows like a hardware and a software story card grouped together. Maybe there's both a software component and a hardware component to that feature. You see what I mean? And nothing says people can't team up within disciplines, so I'm showing a couple of software people paired, working on the software card here in this picture. But the whole idea is people can pair up to do whatever parts they have the ability to do. So even though everybody, the point I'm trying to make here is even though everybody doesn't have the ability to do any task on the board, that does cut down a little bit of your flexibility for moving things along. But the benefit that you're really getting from the storyboard in this case is the visibility and the conversation starters that it brings. So I want to say a little bit more about Kanban boards, but first I want to give you an even more extreme example. I had a client some years ago that asked me, what should we do about our sensor teams? Because they couldn't see a reason to use a storyboard at all with their sensor teams. And what they meant was, this was an industrial controls company, and they often designed specialized sensors for the machinery that they needed to control. And they would typically have a really small team, like maybe only 3 or 4 people. But each person would have a really deep specialty. As an example, they might have an electronic engineer, they might have a mechanical engineer, a physicist, and maybe a software person. So these are each like a team of one, you could think of. They're not going to just pick up each other's work just because they happen to be working on the same project, right? The software engineer isn't going to just figure out how to do material science. It doesn't happen that way. So my advice to them was, well, don't worry about cross-skilling. Don't worry about that, but have the people work together at least part of the day. They also didn't have people like fully 100% dedicated on the project. And I said, well, see if you can dedicate them so they're all together at some portion of the day and they can talk to one another. So the idea is to communicate and communicate frequently. And you could even have a Kanban lane for each of those people just to help them keep their work visible and synchronize with one another, because that's really all they need to do. Does that make sense to everybody? Yeah? So the visibility helps. I just want to say one more thing before I move off of this part of the topic. Here's another picture of the Kanban board, but I've kind of shifted the view a little bit to the left and showed some more columns that are upcoming. So to the left of sprint backlog here, you'll see that there's some visibility for what's coming up in the next sprint. And it might not have been yet fully estimated, or they might not have cleared up all the questions they have on those. To the left of that, it might show more of what's in the main backlog. Here it is over here. And you don't need to have a gigantic main backlog, just enough for the next several months. But what you want out even further upstream is some ideas and analysis. So that can be a place where you can make visible what new features you're thinking of adding later, or things that people have suggested. It doesn't necessarily mean they're definitely going to go into the product, but by just making it visible, you bring out relevant experience that some different team members might have that maybe nobody even knew they had. You see what I'm saying? You make it possible for people to self-organize whenever you raise the visibility. So that's why it's a really good move to increase visibility when you're a little bit unsure of what to do. Just as a side note, I wanted to mention this, I put the note on the slide here. Just wanted to mention, it's not really a Kanban board if you don't have a WIP limit, work in progress limit. And if that's a new concept to you, do yourself a favor and look it up online. There's plenty of great materials. I don't want to segue off into a tutorial about Kanban boards, but I do think understanding the WIP limits and why you should use them, it's a very simple mechanism that drives an awful lot of the right behavior, and it prompts you to ask a lot of the right questions. So it's one of the things I like a lot because of the simplicity of it. Okay, so I'm going to move on to the next thing that gets in the way of hardware-software cooperation, and that is this business of long hardware cycle times. First of all, that's always been true before Agile, with Agile, without Agile. That's not different. But there are a lot of mitigations for that. It's not new that we've had programmable hardware in various forms, and we've had quick turn boards and vendors, that will do something, like on a day's notice. Sure, you trade off for that. It costs a little bit more money. So these programmable hardware things like PLD and FPGA, they usually cost more than what you wouldn't want to put them often in production boards because they're a little too expensive. But they give you the flexibility you need during development so that you can really make up your mind what your final circuit needs to be. And then you can get an ASIC made, application-specific IC. You can get that made for low price, volume kind of prices. All right, so I'm showing, we have a whole bunch of little segments in the green bar to show the software happening in little iterations. But so what I'm trying to point out here is you've got a whole lot of little junctures, like every couple weeks or so, where the software is completing a sprint, right? Each time the software completes a sprint, that's an opportunity for the team to improve what they're doing in the software area, right? Not too many people think of it as improving the hardware also, but it really does. I'll give you some examples as we go on. But in the old days before Agile, you would have the software delivering in long segments, kind of like the electronics. Might be 3 months, might be 6 months, right? Is anybody familiar with that from way back when? Yeah, I see a few nods. Okay. Okay, so what happens is at each one of these junctures where software completes is there's a chance for you to improve something with the hardware. In our case, for instance, we found sometimes that our computation algorithm would go to a state where it didn't complete, and that didn't make sense to us, even though we could be certain that we had implemented the math correctly. And what was happening there, we weren't sure. When we talked to the electronic engineers, they would get on the test points and they'd say, this component or this, part of the circuitry is out of spec. The voltage is too high or it's too low or something. So that would be specific to the one hardware set. So what we could do when we found that out, we would find it out very quickly because we were going on short cycles with our software. And when we would find out those kinds of things, we could make a change. We could monitor that spot and help create feedback for the hardware people. See what I'm saying? So we could do this at these very short junctures every couple of weeks. And if we were creating some hardware, we were monitoring a voltage point, we could give them information long before the end of their iteration, right? They might not be planning to upgrade the board for another month, but they could start learning more things about it than they would have if we weren't going in short spurts with the software. Here's a picture of just a little schematic idea here of how our hardware was evolving. And I'm showing this just to give you a sense of this. This doesn't really change very much with Agile. You still kind of move to your different configurations of circuit board. But this is what we did on this spectrometer project. What we had was we began with an evaluation board. And the little chip that's shown up there in the corner, that's just to represent that the microprocessor also was new in this project. So it was going through revs pretty frequently. we were finding out quite early that a number of the peripherals didn't work on there, so we had to work around it. So like most embedded systems teams, we were initially writing some software and having it work on our desktop machines before hardware was available. And then as soon as we started getting some hardware and got the evaluation board, we would start seeing, okay, how does the real processor behave? So that went through some iterations. And if you look at the third one in the picture, that's where we started adding our own board with our own custom circuitry, right? Because we had engineers we were working with who were building a sensor. You know, because remember, it's a spectrometer, so you illuminate a sample with a known light source, and the light signal coming in to a sensor then becomes the input data for your algorithm. So we needed a prototype board to hold our sensor, and that was fine because the engineers who developed the sensor were looking for some feedback. Okay, so we did that. Next evaluation, or I'm sorry, the next configuration, we added some little motors you see over at the side, because it's just like a camera. You know, you've got shutter speeds and exposures, settings, and things like that. So we had these little motors to work the shutters. And then we went on through a couple more iterations where we're trying to unify it all on one board and have it ready for final production. Now, this is something that doesn't really change with Agile, except that I will say what changes about it is that at each step of the way, if you're working with an Agile software team and you're the hardware guys, you've got some better, more thorough information at each one of these stages for you to go forward with, you know, because of reasons like I mentioned a minute ago. The example of us being able to monitor test points for the hardware people, for example, and just other things that we would discover about the hardware and software interaction. See what I'm getting at? So you still kind of go through this, you still have an evolving hardware platform, but you're not doing something new every couple of weeks. So that's just, that doesn't happen.
What in the diagram does prototype A board refer to?
Prototype A board.
Is that
Number
chip?
5 you're talking about?
No, the text at the bottom, it says then added a hand-built prototype A board, etc. So does that refer to the chip?
Oh.
The Proto 1 board? I'm just trying to.
Oh, I'm sorry. Yeah. Yeah, sorry, I haven't got the labeling that consistent. Yeah, we're just talking about moving from number 1 to number 2 there.
Okay.
We'd keep moving on. The hand-built prototype is called Proto 1 in the third image. So that's our own prototype board that we'd build in-house. And then later, we might have a vendor build it if it gets fancier, but usually it was something we could just build in-house. Okay, but you're going to have all kinds of variations of this, depending on what you're building. It might be something that people just put together in the lab right there at the company, or it might be, they might have technologies on there where they can't do it in-house, and they'll use a quick-turn vendor or somebody, you know, like for surface mount technologies or for multi-layer boards. Okay, so, but the same principle applies. You're evolving it step by step, and you're trying to go in as few steps as you can, really, because each step costs money. And at each one of these junctures, we also have to make a decision, are we going to stop supporting the hardware from 3 revs ago? You see what I'm saying? So if you get through your whole development period with, you know, maybe 5 different revs of hardware instead of 10, it's just less, you know, less of that. Oh, that makes sense? Okay. So we needed to have our software be ready to respond and support the evolving hardware. Okay, we needed to be able to troubleshoot very quickly and effectively. And this was something that was always on my mind from years back, because this is the place where you just lose a lot of time and you tend to do a lot of thrashing. And so what I did is I envisioned something like this. And let me talk to you about what is new with Agile about this. First of all, I'm just going to, for the moment, I'm just going to talk about the top 2 boxes in this figure here. If you look at the upper right, I already mentioned how typically embedded systems teams will start with building their software when there's no hardware available, right? So we just build it using a laptop or a desktop machine, right? We do some initial work. Whatever can be built, we start on it. Maybe design some interfaces, get some early code running. As soon as there's hardware, typically embedded teams will focus entirely on the target CPU. And since the deliverable is the whole system that you're building, you focus on building the whole system, but for the target PC. Now, where we diverged as an Agile team is usually traditional embedded software teams, once they move to the target CPU, they don't ever bother making their software runnable again on a desktop machine. It's not the focus of attention anymore, because the whole point is we're going to deliver it on the target PC, right? So we tend to do our development and debugging there. And as the code base starts growing and changing, people let go of the ability to make it run on a desktop machine. Does that sound familiar to anybody here? You done that? Yeah, I'm seeing some nods, yeah. Okay, so that's familiar. Now, as an Agile team, let's focus on the bottom two boxes in this picture. On these bottom two boxes, here's what we were doing. We would take the C function routines, think of the lower right. First of all, we kept our ability to run everything on the desktop machine. Now, that sounds a little crazy, but it really wasn't as much work as I thought it was going to be. But part of the reason for keeping that is I wanted to be able to immediately slice away hardware versus software problems, right? So if there's something wrong with the hardware and we weren't sure if the software has a problem or if it's something with the underlying hardware, we could immediately just try it on the desktop machine. Now, the problem with doing that is it wrecks your timing. You're not going to have the same timing as you'd have on the target machine. But you can usually pretty easily segment those issues away. They don't usually tangle up with the other things you're trying to troubleshoot. So, okay, so that was the reason for it. We wanted to immediately separate hardware from software problems. But then looking from the verticals, we wanted to be able to isolate a defect to one part of the system. So if you look across the bottom there, we're talking about running unit tests. We're all familiar with that from Agile. And I'm just talking about regular Agile unit tests here, right? Now, so we were coding in C and some assembler. So we had tests that we wrote. We were doing test first. I don't think you'd call it proper TDD. It's kind of an early version of that, if anything. But we wrote a test either alongside of our work on any function or immediately afterwards. We didn't always test quite before it like we wanted to, or at least like I wanted the team to. And of course, the box on the lower left there, we made them runnable on the target CPU as well. Those mid boxes, where it says domain, this is where we wanted to be able to run a segment of the system that's bigger than a unit test, but it's not the full system. As an example, we might want to just run the set of functions that compute the algorithm and give us a result. We might want to run just the set of functions that operate the serial interface. Okay, so that way, if we had an issue, we could localize it to some part of the system, something, higher up than a unit test. So this was part of the foundation we had in place to let us quickly zoom in on issues with the software. We had a couple of other mechanisms too, but this is really key. Now I want to talk about the issue of rework economics and how that feeds into this too. Because everybody knows that in hardware, you have a substantial period of time, let's come over here. You have a substantial period of time where it's very clear to you that you're doing some preliminary work, you're getting ready to build something. There's a period of time where you're planning out the concepts, and you're working on paper, you're making net lists, blueprints, or whatever, but you're not bending any metal, you're not cutting any traces yet. There's a pretty definite point in time when you start actually building anything in hardware, right? Even if you know you're going to revise it. With software, it stays malleable till practically, the nth degree, right? Because even though you're coding, and maybe you have some conceptual work and then you start coding, don't think of coding as analogous to the production side of hardware. Because in coding, you're still doing a lot of detailed design. You're still perfecting the instructions that you're giving to the compiler and the linker. And it's the compiler and linker that produce the executable image that you're actually delivering on your silicon when you send the product out. So if you think about it this way, the economics really are inverted for software compared to physical products. And so this is what prompts everybody to think, I need this design period. I can't really give it up. and especially, in engineering, you're really taught that that's the mark of a professional, and they don't just jump in and, hack around. Okay, so I want to tell a little story about how we dealt with our EE guys for one interface that we decided we needed. And we did this instead of spending, I don't know, maybe a couple of months really trying to work out a protocol totally in advance. What we did here is this, if you look at the right-hand side of the picture, you see the software team in blue, and their software obviously is running on the microprocessor. Now, at first we didn't have this concept. We were thinking, well, the data, we'll just clock it into the main processor, and we'll, compute the algorithm there. But once we looked closely at that, we knew that there was no way we could do that. It would take too many floating point operations per second, or, too many CPU cycles beyond the capacity of any processor, as it turned out. So we had to talk with our EE guys, and they said, okay, we're going to have to offload some of the processing. This is a very common thing in any kind of system. You need to offload some processing. See, the data for each reading would come in as hundreds of pixels, and we couldn't have hundreds of interrupts hitting the main processor for every single data reading. That was insane. We just wanted to come in with one interrupt. We'd bring in the whole array of data, park it somewhere, then give one interrupt saying the data's in, go look at it. That's the idea. So we said, okay, so we need an architecture. So this is how we worked out our architecture. We said we need an architecture that's going to let us offload some of that data receiving, and we'll do a little bit of data conditioning at that point too. So the hardware guys said we're going to use a programmable logic device, PLD, and we're going to figure out a protocol between that and the main processor. Now you might ask, why do we need a protocol? Okay, well, because it isn't just a matter of the main processor asking for, give me a data set, and then poof, you have a data set. It's not like that. You have to tell the hardware, hey, I want you to take some data. Oh, by the way, use these settings for the data. Okay, and move the shuttle to that position. Oh, all right. But then you don't just magically have the data already. The hardware needs to wait a period of time because shutter's a physical thing. See, if it was a software-only system, we'd be asking for the data, like a microsecond later, when hardware didn't have a chance to actually physically move something. So what we do is we have this little dance. It's a protocol, so we cooked it up, okay? And this line that you see between the two green boxes, that's meant to show some software that we were putting in place, and that software would be the living specification of the interface, okay? So the way the software was going to work is we'd make up what this protocol needs to be, okay? So part of the protocol would be the hardware brings in the data. Once the hardware has finished loading the buffers, it has to signal the software. Now you can go look at it, because without that signal, we'd go look at it too soon before the buffer was fully completed. So you see what I mean? There's a sequence of steps, and they need to be done in the right order, and each side has to tell the other when it's clear to go do their part. So that's why it was like that. What we did with this piece of software that you see in the middle there, we wrote that up at first as a way to mock in what we didn't have. So if you were one of the software people, the little blue team there, that would accept your request to go get some data, and it would populate the software by itself without any hardware connected, would just populate a set of dummy data into a buffer for you. Give you all the rest of the signals the same way you're supposed to send them, because that was a living specification of the interface. Okay, and then what would happen is, so we, the software team, could use that interface to do the interaction that we wanted to do. And we would just flip a compile switch to have the interface fake in the responses from the hardware. You could flip it over, and for the hardware guys, it would do the same thing. For the hardware guys, they could run that interface software without us, without the main processor even in the picture. There might be just the board on the left. Okay, so the hardware guys would just be on a board with their PLD by itself, and they could, well, I shouldn't say by itself. They're really talking to this bit of software running on the main processor, but we wouldn't have any other logic behind it. You see what I'm saying? And so it would dummy in our responses. And when you flip the compile switches the right way, it would be the real interface, because it was all the same code. So at first I was a little reluctant to build this, because I thought, oh boy, this is how things go off the deep end, and you put a lot of effort into something that doesn't go anywhere. But it probably took less than 2 weeks of my time, and maybe me and part of another person's time. So to just give you a sense of the effort. But because we did it early in the project, and because we were in dialogue building this, we got a lot of payback out of it, okay? This thing probably paid back the effort over 100 times, literally, because there were so many times when we had to do something with that interface, and we needed to be able to quickly check, is it still working, do we break anything? So this was a real big payoff for us. I should mention over there at the left, that's showing like a sample that's being examined, be illuminated by a lamp. That's part of the instrument. Okay, and then the data comes in through the sensor I already mentioned. We had engineers that were building the sensor, and they needed some feedback because the mathematicians didn't know yet what raw data was going to look like coming in through this instrument. See, the issue with this project was everything was new. The concept, the spectroscopy concept was new. The sensor was newly designed. The microprocessor was new. We were the first port for that microprocessor. We were the first port for the operating system that we were using. We were using a commercial OS because we needed a real-time system underneath our software, okay? So anyway, so this is how we implemented some software that basically mocked the interface from either side, and it acted like a living specification. Sure, we did have a paper document to show the specification because people insisted on it, but the program was the real specification that we made work. All right, let me move on a little bit. This slide is just, the part says challenge and action is just what I've already mentioned. It's just another description in words. Let me tell you a little bit more about the result. So we found that changing by either the hardware or the software side of the interface, we could fully test all the activity, like within about 30 minutes or so. This was really great. I mean, if we had, instead of building this little piece of software, if we had just used paper specification to work things out with one another, it would have taken a lot longer. We would have been discovering issues pretty late in the game, and there had been a lot of activity to clear up confusion between us and the double E's, right? And there'd be some temptation for blame and finger pointing, which I know never occurs in the real world. But we didn't want to have that. Another part of the result surprised us a little bit. Let me just say one thing here, back here. I want to mention a big goal for the hardware team is eventually we wanted to use a ASIC and not a PLD, right, in our production because for cost reduction. And the goal here, well, it would be a bad thing if we paid for an ASIC more than one time. We wanted to only pay for it one time because it's a big ticket item, right? And so that's our goal. We wanted to work this out thoroughly enough, actually use it enough that we had confidence in it, that we could use that interface well over the next coming months of development. So the question is, did we or didn't we achieve that? Well, we did avoid any rework. We sent the specification out to a vendor, to build an ASIC. They sent us back some code to try. It was their understanding of our spec. And as I remember, this was like less than an hour. We had run it through our test, because we had software. We used that little program. We turned around and answered to them, shipped it right back like within an hour, and they were flabbergasted because we identified a handful of places where they had it wrong, and they didn't understand how we knew that. How did you figure that out so fast? And we said, oh, well, we have this little simulator program. And they said, wow. And we said, well, here, we'll send it to you. You can just try your next rev with that before you build the ASIC. They were making sure they understood what we wanted. And so that was great. So they were able to use that as their specification and just build the ASIC one time. So that was a real time saver for us. So I want to talk about some of the benefits that surprised us next. We had, like I said earlier, frequent software releases did create many more opportunities to improve hardware and software interaction. One instance I already mentioned was the software monitoring of test points for the hardware. But there was another wrinkle that came up about that software monitoring. When I asked the hardware guys, okay, we accept that when our code is running on a different machine, one machine might be out of spec compared to another. So even though it's the same identical software, the algorithm might not resolve on one machine when it would on the other. And they said, yeah, and so we said, okay, so that could be because of, some voltage level or whatever being out of tolerance, fair enough. I said, so let us put in our power-up self-test or in our some sort of repeated testing, making sure that the voltages are in the right range. So I asked, what range should it be? And they said, well, we're really not sure. And of course they weren't sure. Why? Because everything in this project was new. This wasn't like a rev of a product where we had a lot of history. They weren't sure. They didn't have the history and the data to really say with much certainty. And so another area that we were able to help them is that we could, with that monitoring, we could save up data or help them save it up. We had, something like 40 or 50 units that were circulating with advanced customers. So there was opportunity, these units were being used in the field. We were using this as a way to get feedback, on it and build customer interest. So, we could put in this monitoring, we could put enough of it in so that we could give them a graph and they could see what their voltage levels are behaving like in real world conditions. So that was a big help to them. I'll mention another area that surprised us in terms of the benefit it gave. Late in our development, around the point where we were trying to get everything buttoned down for volume production, there were anomalies were down to very few. And I should also mention that throughout development in this project, we never had more than 2 open defects. And that's because we had many layers of defenses to detect any sort of anomalous conditions in the code. I didn't go into that in much detail tonight, but we had many layers of defenses. So anything that got to integration test or later, and it was either a defect, an unwanted behavior, or an unexpected behavior, got logged as a bug. So we had very few. Like I said, we never had more than 2 open defects at any one time. But when we came to the end and we were trying to go for volume production, we had a small handful of anomalous behaviors in the field that weren't really bad in terms of the data collection, but they were bad enough that they would mess up the statistical reliability of our instrument, for having it become more of a standard. So the question was, what are we going to do about these things? So I remember one of them where it was just a small voltage level shift, and we couldn't tell where it was being introduced, because the problem was it wouldn't show up when you just looked at the, if you put a unit on the bench and you just ran part of the system, it wouldn't show up anymore. The whole thing had to be running, and you know what I mean, like under field conditions. So the other engineers couldn't really get at it and couldn't really get the clues they needed. So what we did was, as a software team, we had the ability to turn around a reliable release in less than a day. So what we started doing as a software team was we said, what clue do you need? We'll capture some extra data and we'll stash it, and then you can run with that and you can see what happens. And they would tell us what other information they would like to be able to probe, and we would produce a release the next day, and then they'd meet and do some experiments, and then they'd ask for another clue, and we'd put in another clue, a different one. So that's what we could do. So what was happening is, after a few weeks of this, they had really wrung out all of those oddities, and they had solved them. So what was happening is, we as a software team were becoming a reliable enough tool for the rest of the engineering team to use to debug those system level issues. And there's one last one I'll mention here. There were dozens of issues like this one, or I shouldn't say issues, little incidences like this one. And I just want to put in one of them here because they had a cumulative effect. So in this one little thing, I'll just mention this. The units were being assembled by hand, right? Because we had just a small number of them being tried out in the field. And so, but we as a software team, we had a little laboratory area where we had the hardware, and we our cubicles were just around the edge of this lab. So we were all working together pretty much. And in the room next door, we had people that were assembling these units to go out to the field, you know, as a new one needed to be made or as older hardware needed to be upgraded. So what was happening is one of the people was saying one day, gee, it's a pain because it takes 20 minutes every time I need to test the lamp. And I asked, what do you mean? Why does it take 20 minutes? And he said, well, when you first fire up a new unit, it goes through the power on self-test, and there's a little bit of warm-up time and all this. It ends up being about 20 minutes before the natural part of the cycle comes around where the lamp turns on. You know, and his need was to just make sure the lamp was working in the unit. And I said, oh, well, that's something we can do easily. We have all those drivers, the lamp, the shutter, anything else. We have those little drivers. In fact, we even have it so that, remember I showed that slide where everything was segmented? Any one of those things could be downloaded to the hardware, to the target processor, or run on the desktop machine standalone. You could take any single modular function, run it standalone with its test. We could take any task in the system, like the math algorithm, run it all by itself. And we had other software that would feed it what it needed and look at what its outputs were. That was what I meant when I said we could segment it that way. Well, so we had all these drivers, and so I said to him, well, we can easily put together a little menu. It's a different image than the image that you're going to ship the units with, but you can download that image, and then on this menu, you can just pick turn on, turn off as many times as you want with the lamp. You can pick move the shuttle here, move it back, move it there, move it back again. You know, you can do anything that the drivers need to do for the whole unit. We could just string those together. It was almost nothing for us to do that. And we did that early in the project for the electronics engineers too. The way we had worked before and the way I've seen a lot of companies work is the EEs have to write the drivers because they are stuck with the job of checking out the hardware early in the game when it arrives, you know, and the software people haven't gotten around to writing their version of these drivers. So, you know what I mean, you're doing duplicate work with one another. So anyway, this is just a small thing. This was a really small thing, and there were many things like this where we just happened to get wind of it because we were close to the other group, physically close, like not just in the same building, but next door. So part of the reason I bring this up is that there's so many people who think that it doesn't cost anything to have, you know, your people dispersed, you know, whether it's offshore or people on a different floor in the same building. It really makes a difference. There's a lot of these little happenstance things that just never come out. So, oh, wait a minute. Before I get into this, I want to ask you something. I want to ask you a question. So when you're working with software and hardware people, I bet you sometimes have a mystery bug, right? Where you don't know at first, is it really hardware or software? You can't pull it apart, right? Because you haven't got that dual targeting arrangement that we had. So in your company, I want you to put up your hand if when there's a mystery bug, the hardware people are willing to go look at it first. Does anybody have that? Okay. How about, let's try the other test. In your company, when you have a mystery bug, do the software people have to go and check it out first? Are there any hands up? Yeah, I see some hands. Look at that. Okay, so I noticed that was a law of the universe. I noticed that some time ago, and I wasn't about to challenge it. I wasn't even trying to. One of the things I found out, I just noticed it, I don't know, in the lab, one of the hardware guys was, you know, working, and something didn't add up. What he did right away was grab one of those little drivers we had given him, and he was checking his hardware. And I thought, wait a minute. He was just automatically questioning whether the hardware was working. He wasn't coming to us and saying, prove your software is good. And I thought, oh, so he's taking it from the opposite side now, and he's a hardware guy. So the hardware now is guilty till proven innocent, when it had always been that the software was always guilty till proven innocent, right? And I just figure it's because software is a younger discipline than hardware, maybe. But when I noticed that, I thought, wow, that's pretty amazing. Because if I set out to have that happen, I don't know how I would have achieved it. you know? I mean, this just sort of happened without any big fights, without any screaming, you know? So this was a big surprise. Another thing that kind of surprised me too is that it was really only the software team consciously trying to use Agile practices. Why? Because I was yapping at their heels. Okay, I'll confess. But I did convince them on the merits, pretty much, to at least give these practices a try. And then the practices really proved it. But what ended up happening was that the hardware became a lot more agile without trying, so to speak. It's really the leakage that I mentioned at the beginning of the talk, where I said because the software was going in these small steps, each of those steps was a chance to improve not just the software, but the software and anything else it touches on the team, right? So not just the electronics, but the mechanical aspects, opto, any of the other kind of hardware that had any interaction with us. That's why it became more agile, and they didn't have to try to force their work into 2-week increments or anything like that. There was never any conversation with us telling them you should do 2-week sprints. We didn't do that. We just tried to be as useful as we could for the hardware people, and I don't know, just made it a two-way street, making progress all together. Let's see, so what else do I have here for us today? I have some tips and caveats. Let's talk about that. Okay, this is something that everybody that I deal with has come to the conclusion. When I say everybody I deal with, I talk with lots of other people who are doing software hardware products, and some of them doing like pure hardware products, for instance, chip design. And what they found is even though they couldn't speed up the, I shouldn't say speed up, they couldn't do a real shippable increment of new silicon on a 1-month pattern, okay? It typically takes a year, 18 months. But what they could do is make visible their simulation to their customer and cross-check with that. So they could do some steps like this, but the key thing was they needed to have working hardware at every juncture. Okay, so these guys that I know that were working in chip design, their juncture was 1-month increments normally. They wanted to do an update between their hardware, their software, and their customer. In other words, they wanted to validate their simulations as far as they could. For them, it was really important to have at least the working simulation ready to go and everything associated with it. Other people doing software hardware in a style like what I described in our instrument project, they've also concluded that the one thing that moves them along really well is to have these increments where they've got working hardware at every juncture of the software iterations. So what I'm saying to avoid is you don't want to go for a period where, the software's got to go for the next 3 sprints with no hardware working because somehow we got caught out and we don't have any units in-house. There's no working hardware to try it on. You just don't want to have that. Okay, another thing is building key interfaces really early. I described one, and that's not the only one we built in a similar way, but there were others that needed a really different tactic than what I described. But if you get at it early and you prove out those interfaces, the trick is to just prove out the interface early. You don't have to plan all the details of what's inside every entity, but you do. Think of design by contract. That was a great concept. It came around a long time ago, but it's still got a lot of validity. It's just that a lot of engineers are trained to think that they're not doing a legitimate thing unless at the point where they think they've defined the interfaces, now they feel they have to go on and design everything that's going on inside every module. And that's where I'm saying, no, you don't quite have to right there. It's better to come up with a concept for the interface and now make that work. Just make that interface part work. And the other things that you might have to do to flesh out all the interior stuff, you can kind of do that interactively, or you can do it a little bit later, because that should be the things you have more confidence in anyway. You want to use the simplest tooling possible, and you want to keep it under the team's control. I didn't say too much about this in my examples, but one of the things I did as tech lead is I shopped around for us to get an operating system that was proven commercially, that could run on the desktop or on the target hardware. And there's a lot of techniques you can use today that'll help you do something similar. But I looked for that, but I also wanted one where they would give us the source code, and make it available. Why? Because I knew that since we were the customer for the first port of the OS to that processor, we were going to have to debug some things that might lead into that code too. And we did, you know. So I didn't, in other words, I want us to be able to chase a bug into the OS code, back out again into our code, back into the OS, and we could chase the bug and not be at the mercy of a vendor's service department, okay? Not that I think they're bad or you know, aren't going to do anything evil. It's just that we've got the sense of urgency and we want to keep it. So keeping the tooling simple, keeping it under the team's control is really important. With very simple tools, you can get an awful lot done, especially if they're under your control. Team lab space is so critically important. Now in our case, the hardware guys were adamant they didn't want to share their lab with us. And it's not because we did anything bad. They just knew that they used the equipment in a different way than we did. But you know, I wanted us to have a team room. So what we settled on worked pretty well. The hardware people had their own lab space, and we had a lab for the software that was not too far away. And we'd each have, you know, hardware and the software, and we'd have various connectors and all that sort of thing. But you know, you could go away and you could leave stuff in some state and know that when you came back into the room, people hadn't cannibalized it for some other purpose. So just having some hardware space and having some rules of the road. And that's another thing, I didn't put it on the slide here, but being able to deal with what's often called the soft skills, not having to fight things out, okay, as a team, being able to make a decision and carry it out. And sometimes that means you support a decision that maybe you weren't so hot about, but you know, you acknowledge that it has some merit and it's worth a try. Just getting a team to that point is huge. So I just wanted to say a little bit about that. And I think I'm done, except for being able to answer some questions. So here's a little bit about me, but I'm going to put this next slide up now because I just firmed up a whole bunch of dates. Oh, you know what? Before we go into questions, I want to point something out here. This is a webinar, which in a month's time, so feel free to sign up if you're interested in finding out some more about hardware, software, agility. And this one's going to be right here in Boston. Look at the Software Design for Medical Devices conference is going to hold their conference in January here in Boston. So you may want to check that out. I will be giving a talk there. Myself and Brian Shoemaker will be speaking. I often team up with Brian when we're working with a medical device company. Okay, so that's it for some coming events. Questions?
Could you elaborate a bit on your interface software? I think it's slide 18 or 19.
Oh, yeah.
Is that written in C?
Yeah, it was just C source code. It was just C source code. It was a series of function calls. You know, they might be called by the, you know, the hardware, or they might be called by the software. It's just, we wrote them up as a way of making a request from one side to the other, or responding to a request. It's really just implementing protocol that we cooked up.
And it was primarily functional, not necessarily clock cycle accurate, or was it?
Clock cycle accurate. Well, there was timing to be kept. We had a time constraint on how frequently we're trying to bring in the next data set. So there was a timing constraint there. There was the possibility that a data set could be bad, but I don't think we had the front-end hardware smartened up enough to recognize a bad data set. And I'm pretty sure we never tried to do that with the software either, but we did correct for dead pixels in the CCD array.
When the ASEC vendor sent you something to test, I guess I didn't exactly understand what it is that they sent you to test and how you tested it. I mean, it sounds like the software interface to software.
Yeah, I think, yeah.
Not sure what kind of software the ASIC vendor sent.
I think they worked up, I'm a little fuzzy on this now because it's a little bit out of my domain, but I believe they worked up a sort of the equivalent of our PLD, but in their own tooling, something for us to try out. I don't believe it was a piece of physical hardware, but it was them reflecting back to us their understanding of our protocol. from having read it in a document that we prepared.
That they gave you some sort of simulation language?
Yes.
For their hardware?
Yes, it was something like that.
I guess this isn't a question, but
Yeah.
in the very beginning, you talked about obstacles to collaboration between hardware and software teams. And I'd like to suggest that one significant obstacle is the organization that you're working in, where their management team, or their, the structure of the organization makes collaboration very difficult because of the reporting structure that they have.
Well, sure. I mean, everything that is done organizationally to separate software from hardware tends to get in the way. Obviously, it's not intentional, but it just tends to get in the way in very much the same manner as, when Agile was a brand new thing, right? Companies had tests very separate from development, right? And Agile's mission was to, no, we're going to blend them. They don't belong apart. You want to test as you go. So with software and hardware, you want to work out those interfaces as you go as much as possible. So that's why I had that example in there.
When you first pass success on boards, how does that, you think, relate to software, where I feel like the emphasis is much more on having testing so that you can iterate very quickly and catch issues? Versus hardware, which is a very strong push to have minimal design cycles. If that makes sense.
Well, I think a lot of judgment goes into the question of what does minimal mean for the hardware design cycles. Do you see what I'm getting at?
Yeah.
So the folks that have the most experience, they'll naturally bring up the areas that worry them, that where they're not quite sure we can make it that way, and they'll want to exercise that as early as possible, right? Because that's where you've got some maneuvering room. If you wait for the parts that you're not so sure about, that's when you're going to get into trouble. So even though I know there's a lot of pressure on everybody all the time, everyone I coach is trying to do 20 things at once. If you pick the right thing and you think carefully about it and you have the right conversations, I know that for us, we didn't feel like we were working in too much of a rushed way. I'm not sure if I'm really answering your question, but from my understanding of it, it really goes to picking the right battle and sequencing them in the right way, and then focusing very cleanly on what you're doing. Just work one problem at a time as much as you can. I mean, it's all you can really do. Anytime you think you're multitasking, my experience is something's getting shortchanged. So that's pretty much what we did.
I was wondering about comparing the sprint lengths between software and hardware, since hardware has this longer release cycle, and Agile is aiming to be able to adapt quickly to changing requirements of customers or new developments. And software, you do this because it's like 1 week cycles, and hardware, as your slide shows, will have longer ones. So first of all, how do you do Agile in a hardware situation where the sprint cycle by definition is longer, and how do you coordinate Agile hardware and Agile software with this quite a bit difference in sprint cycles?
Well, with the hardware, we don't try to make the sprint cycles really short. We just try to have the new set of hardware up at bat every so often. It might be every 3 months. It might be every 6 months even, although I think that's pretty long for these days. But the whole point there is that you want to have stable hardware available every couple of weeks. It doesn't need to have changed. Okay, so if the software is going on a 2-week cycle, for example, I just want to, as a software person, I just want to know at the end of my 2 weeks, there's some real hardware I can prove this out on. I mean, I want to have hardware, on my desk actually every day that I'm working towards, but I want to know that that's the configuration of hardware that I'm delivering for this sprint, okay? That hardware may not change at all for this sprint, the next sprint, and the sprint after that, but I'm in dialogue with the hardware guys, and we know that the next rev of hardware is going to add certain things, and we're talking about what ways the software needs to be ready for that. And we're having a conversation about whether we want to continue to support the old hardware, or do we need to make a cutoff? You know, are we making a change that really is going to invalidate the older software? Do you see what I'm saying? Sometimes you're changing the hardware in a drastic enough way that you just can't have the same software supported anymore. Do you see what I'm getting at? So it's really just think of layering your hardware. You know, there's a new hardware set coming up, but not until later, and we're going to keep our set. Some batch of iterations of software are going to be on the same platform. Okay, so in that way, we can rev the hardware on whatever its own cycle needs to be, and we're just being careful about when the next version of hardware is up to bat, so to speak. I think you're next.
Just a couple comments on having managed both hardware and software groups together. One of the first things that I found is, I think in helping play together and work together, is their jargon.
Yeah.
That I ran into a number of problems over the years where the hardware people and the software people used terms that were very similar, but had different meanings to each other. And you had to be very sensitive to that when getting started in groups, so that they are, in fact, and then sometimes you had to remind each other as along the way of the project. So the terminology, the communication is one of those things that I found was very important. In fact, more on the technical side, I also found that one of the useful tricks was to have the software people work with the hardware people, and typically what I found was the software people knew how to test things for the hardware people. So the hardware people would actually ask, help me, to the software people, or we could set up a team where the software people actually built the test for the hardware people. It wasn't software people doing testing for their own, but they actually had the hardware people working with the software people to build the test. So it's the design for testing of the hardware, which I think is what you were trying to get at. So very, what you presented was very good.
Yeah, it sounds a little bit like us helping them with the monitoring, you know, where we were essentially providing a mirror in a way to show them some of that more than explicitly testing it. But sure, that's another pattern that will emerge. And I think you make a good point, too, that a lot of these interactions will just emerge. They'll become obvious to people. You don't necessarily have to try and make it happen, but it is a good point to clear up terminology. That's probably a good activity. When I coach teams, I like to have them create some working agreements, you know, of how they're going to operate together, how they'll make decisions, things like that. And you know, maybe nailing down a glossary can be part of that sort of activity.
When your hardware and software are in customer sites around the world, and you discover that you made a design error in the hardware, how do you deal with the temptation to try to set things right by finding a kludge to write in your software that somehow allows the hardware to keep working?
Well, funny you should mention that. I did have that problem. Luckily, it happened during development, and yes, the reality is this, when you've got software out in the field and it's costing the company a fortune each day, that they got people in the field, they've got other things set up by their customers that, you know, their customers can't maintain forever either, you have to just be responsive. So, yeah, once upon a time I thought, well, I'm going to be a good engineer. I'm never going to put a kludge in my code. But what we did was I gathered the team around and I said, okay, we've absolutely positively got to come up with a simple fix for this problem. Let's have some ideas, and whatever is the simplest and surest to work this minute, no matter how ugly it is, no matter how kludgy it is, whatever is the most sure to work, simple to implement, not likely to break anything else, that's what we're going to go with, and that's a kludge. So we would put out a kludge because we needed to get our company's butt out of the fire. And we'd put in a kludge, but we'd absolve ourselves of the sin by making our absolute positively top priority to, as soon as we had a breather, And I mean, like the next day, we would tear that kludge out of the code and we'd properly and thoroughly test everything and put in a proper fix. So we would give them something temporary because you just got to, you know. The company's bleeding money if you don't. You can't just sit around and not respond. So we would use, you know, we'd put our heads together and try to really come up with the best idea. And there was another thing that kind of surprised me too, because I just have this natural aversion to kludges, so there would be certain things I wouldn't even think of. But some other team members would come up with something just wrenching, and by my own rules, I had to admit they were right. They came up with something really simple that would really, really work, and it wasn't going to break anything, even though it was horribly ugly. So yeah, that happened. You just have to do what you got to do in the moment. Yeah.
Nancy, I think we got one more.
Yeah, let's do one more and let's call it done. I'm glad everybody's so interested.
I was wondering if you could speak to your experience about Agile in the medical device world, which is so regulated.
Yeah.
And you lose a lot of it as you pay.
Well, you know, that's it's a common misconception that you have to somehow back off on agility just because you're working in medical devices. I'm glad you asked that question because it gives me a chance to bring out something that I think is really important, and that is a lot of people think of Agile as its main benefit is the speed of development that it gives you. You know, a lot of companies look at it that way. You know, it's pretty good quality, but it's the speed. You know, that's what they want. And I've always come at it from the other side. I came to Agile because I was trying to do super high quality systems that wouldn't fail, right? Because they're safety critical systems. And I mean, I knew what NASA did to, you know, make their systems as reliable as they did, you know, but they had a huge budget and they could put a lot of labor into it. And a real company just can't, so I liked that challenge. But anyway, so to make a long story short, if you make your Agile all about super high quality, I don't mean gold plating, I mean really good solid quality, and you put in those foundations I talked about, those really pay you back. A lot of people are kind of reluctant to put those in at first though, because you know, you don't have stakeholders asking you to do it, really. But if you put those in, you can get very high quality, and the speed will come as a side effect. I did some numbers to compare our productivity to other teams in the industry, and I found that we were getting about 3 times as much work done per unit time, you know, by the team. And a lot of that was because we weren't spending hardly any time chasing bugs and fighting over bugs and managing a gigantic list of bugs. Do you see what I'm saying? We could erase almost all of that because we fought the right battles early. And that's what you have to do in medical devices. It's a common belief that the regulatory aspect puts a lot of burden on people. It can if you handle it in a very static, paper-driven way, but you don't have to. You can use a lot of living specifications like what I showed here. You can automate your testing and have test reports. Documentation doesn't always have to be ink on paper. It can be living specifications. So if you really get with it, there are medical device companies right now that are humming along using Agile fully and using DevOps fully to the max. They're not cutting back on quality. They're not cutting back on speed. They're not cutting back on anything. They're getting every benefit from Agile, and they're staying fully compliant. And another thing to mention, too, is that a lot of people in the regulatory bodies, both American and European, they understand about Agile. And they understand if it's done well, that it's a real benefit. The regs are written, both American FDA and European, the regs are written to not dictate your process. They're written to give them, they're written in such a way that they want to make sure that you can state a goal and then that you're achieving it legitimately. That's it. They're trying not to tell you that you have to use a sequential process or anything like that. So, did I answer your question?
Yeah, very helpful.
Okay. Thank you. That was a good one to bring out. I appreciate it. Thanks, everybody. Thanks.
Will you remind us how people can get in touch with you after tonight?
After tonight, yes, you can go to Nancy V at leanagilepartners.com. It's also on the slides. Okay.
And we'll get the slides, we'll share the slides with everybody so you
Okay.
can see her email address and her website. Also, I can recommend, Nancy, you read this really great article that's published on the InfoQ website about Agile for hardware.
Oh, yes, it was called, Yes, Hardware Can Be Agile. It came out a couple of years ago. You probably can still dig it out.
It's really good, great overview of Agile for hardware. So
Okay.
Thank you for that as well.
Okay, thank you.